remarks. So a quick review of what we've done so far in this chapter. It's all based off of, well, in some ways, the idea of the class equation from the previous chapter. So the first main result we saw was this Cauchy's theorem. So if you have any finite group, P a prime number dividing the order of G, then G contains a subgroup of order P. We already knew this for abelian groups. It had a much easier proof for abelian groups. The same thing is true for groups in general. And by carefully considering the class equation and the divisibility by P of the various bits of it, we were able to prove this. Okay? So every finite group has a subgroup of order P if P is a prime dividing the order of the group. But you can go even further than that. And the first Sylow theorem says not only is there a subgroup of order P when a prime P divides the order of the group, but if any power of this prime, because typically a group will have a size which has a factor of some power of the prime. Typically. Okay. So for any power of any prime that's dividing the group, so P to the R divides the order of the group, then G contains a subgroup of that size. Okay? So that's telling you a lot more. Again, similar approach there based off of the class equation and just a very careful induction argument looking at the divisibility of these things, and we made use of quotient groups as well. Okay, so that's kind of a review of the results we've seen so far in this chapter. So the remaining two theorems. So that was the first Sylow theorem. There's a second and a third. So the remaining two theorems, Sylow theorems, concern the number of such Sylow P subgroups, the number of them that there are, and their relation to each other. Their relation to each other. So, sorry, a definition, I think we mentioned it last time, but we'll do it here. So, a Sylow P subgroup of G is a P subgroup. Remember, a P group is the number of facts we know about P groups. P groups, by definition, are groups all of whose elements have order some power of P. Additionally, now we also know any P group, it's the order of the group, number of elements in it, is itself a power of P. So everything's to do with P and powers of P. So a P subgroup of G means a subgroup that is a P group, and it has size a power of P, so therefore this power of P must be dividing the size of G by Lagrange's theorem. And when the adjective Sylow attached to it means that it's a P subgroup of G of maximal size. Maximal size, okay? So i.e. P to the R divides N, and P to the, which is equal to the order of G. Let's forget the N. P to the R divides the order of G, and P to the R plus 1 does not divide the order of G. So P to the R is the largest power of the prime P that divides N. And so a subgroup, a P subgroup of size PR is called a Sylow P subgroup of G. Okay, we know these exist because The first Sylow theorem says for any power of the prime p that divides the size of the group, there will exist a p subgroup. There will exist a subgroup of that size. So we know they exist. So then the question is, now, the first Sylow theorem doesn't say there's only one. It just says that there is a. So typically, we'll expect that there might be many different subgroups of that size. So there could be a few different subgroups of that size. So the two Sylow theorems go some way to completely describing that the system of Sylow p subgroups. Okay. So the number of them that there might be, for any prime p dividing the size of G, G might contain a few different Sylow p subgroups. So what's the relationship between these groups to each other, and how many of them are there? These are the two questions that the second and third theorems seek to answer. Okay? Now this relation is through, this relation meaning this one I'm talking about here, how the groups relate to each other. This relation is through our familiar idea of conjugation. But now, not conjugating individual elements by an element from the group, but conjugating whole subgroups. Okay. So there's a basic fact which I think we would have proved when we looked at subgroups, or it might have been one of the exercises. We'll return to it again. But it's a relatively straight exercise to show for any subgroup K, say within a group G, the conjugate G, K, G inverse. So if G is an element of the group, okay, you can conjugate the whole subgroup by G. Now this is kind of like the notation we use for cosets as well. So the meaning of this, of course, the meaning of this is the set of all G times little k times G inverse for every little k in the subgroup K. Okay, it's quite clear that that's what it means. But we're conjugating the whole set K by G, G, K, G inverse. And so the fact is that this is again a subgroup. So the conjugate GKG inverse is again a subgroup. Again a subgroup. And also it's of the same size as K. Because when you operate on group elements by multiplying by some particular element, that's an injective operation. So one-to-one operation. So the amount of things in this set is the same as the amount of things in K. If two of these for different Ks were the same, so if GK1 G inverse was the same as GK2 G inverse, it would have to be that K1 is equal to K2 because you can cancel all the G's. Okay. So that's the basic fact. If you have some subgroup, you can conjugate it with any element from the group at all, and that will give you a new subgroup of that. Well, maybe not a new subgroup of that same size. It'll give you a subgroup of that same size. It could be that this is the same set as K. Well, that's the definition that K is normal, of course. Yeah, a normal subgroup is one for which GKG inverse is actually equal to K. But typically, the subgroup will not be normal, and so this will be a different subgroup of the same size. And so we actually have, and this is what he introduces at the bottom of page 242, so we actually have an action. By any subgroup, say H contained in G, on the set of subgroups. On the set of subgroups of G. Okay. So you can have a set of subgroups of G. For any subgroup, any subgroup of G, or typically G itself, you got an action of G on its own set of subgroups. The definition of the action. So you take an element from the group. What do you mean by that little element acting on the element in the set you're acting on, the set of subgroups? Well, we're going to conjugate about that little element. Okay. So this will move the subgroups around amongst each other. And this is the action that the second and third Sylow theorems study. So before we launch into looking at the proofs of these, just a little bit of terminology. So because this is an action, you can talk about the stabilizers. So the stabilizer of a subgroup say K under this action uses H in its definition, but I think it's more natural to use K since K is the one we've been thinking about operating on. Stabilizer of a subgroup K under this action. And just as before, when we were considering conjugation of the elements, we gave a special name to the stabilizers. They were called the centralizers. Very often when you look at special actions, there's a special name for the stabilizers. So the stabilizer of a subgroup under this action is called its normalizer. And that's a sensible name. So the definition of NK, this will be the set of elements within the group G, such that GK, G inverse. Remember, the definition of the stabilizer is such that when you act on the element, when you act on the thing with the group element, it leaves the thing unchanged. So we're interested here in seeing when GK, G inverse is equal to K. So this choice of this word normalizer is sensible because this is the relationship that has to hold for any little g in order for the group K to be called a normal circle. A couple of basic facts about this is certainly K is contained in its own normalizer. If you take any element from K, consider conjugation. So that's the case where the little g is coming from K. When you conjugate a subgroup by one of its own elements, you're just mixing or moving around the elements in the subgroup amongst each other. Okay, and the subgroup is closed with respect to the operation, so all the elements are just going to move around with each other. So K is certainly a subgroup of NK. Secondly, K is normal. Not necessarily in the whole group G, but it's normal in the group NK in its own normalizing. Because by definition, the normalizer only consists of elements such that when you conjugate K by this element of G, it's still K. And that's the definition for the group being normal if this holds for every element little g of the group. So we can say that K is normal in its own normalizer. So it will be possible to consider quotients. We'll be able, and they feature in one of the proofs where you consider the quotient of a normalizer by the subgroup. And in fact, NK is the largest subgroup of G containing K, which has this property for which K is normal. Is normal in it. Okay? K is a subgroup. There will be larger subgroups containing it, and in some of those, K will be normal in that subgroup. The normalizer is certainly one of those such things, one of those subgroups containing K, for which K is normal in it. In fact, it's the largest such one, okay? Because it consists of everything for which that normal criteria is true. Okay, so that's just some basic ideas, review, and terminology that's needed before we go into looking at the proofs of the second and third Sylow theorems. Any queries about that? Okay, so I'm going to switch to looking at using Judson's online text now. So let me just bring it up. Mirror instead. Where's it gone? Mirror extending. Good, we're back. Okay, so go to Sylow theorems. Okay, so first let's just look at their statements. So remember, these are described with a Sylow P subgroup. So P subgroup of the group of maximal size. So the second and third give us a lot of information about how these different subgroups relate to each other and how many of them that there are. I mean, it could all be coagulated into one result, but traditionally they're separated out like this. Okay? So the second one says basically that all the different Sylow P subgroups for a fixed prime P dividing the order of G, they're all conjugate to one another. Okay? So that's just what it's saying there. So G is a finite group, P is a prime dividing the order of G. All of the Sylow P subgroups of G, could be many, are conjugate to one another. Okay? So P1 and P2 are two such Sylow P subgroups. They're going to be conjugate, meaning there will be an element G from the group such that G P1 G inverse is equal to P2. Okay? So remember, conjugation of any subgroup is again a subgroup of the same size. So this will again be a Sylow P subgroup, certainly. When you take any Sylow P subgroup, conjugate it by an element, you will get another Sylow P subgroup. Yes, you will get another Sylow P subgroup, but this is saying that any two Sylow P subgroups will be related through this. Okay, so that's describing how they relate to one another. The third Sylow theorem describes the number of them that there are. Now, it doesn't just tell you exactly what the number is, but it gives you conditions that the number has to satisfy. They're very interesting conditions and very kind of number theoretic type conditions. Okay? So if G is a finite group, P is a prime dividing the order of G, so there are Sylow P subgroups in G. The number of them that there are, there's two facts about it. Number one, it divides the order of G. That's interesting. That was the idea from Lagrange's theorem. Remember, the size of a subgroup must divide the order of G. But here we have something quite different. The number of different Sylow P subgroups that there are has to be a divisor of G. And secondly, whatever that number is, the count of the number of different Sylow P subgroups is congruent to 1 modulo P. Okay, so those are two key bits of information about the number of different Sylow P subgroups that there are. And together with this fact that any two Sylow P subgroups are conjugate to one another, this can give us very interesting conclusions about the nature of subgroups of a certain group based only, when we only know the size of the group, by applying these theorems, we can nevertheless draw some very interesting conclusions about the group and about its possible subgroups using all of this information. Okay. Now you'll see beforehand there are a couple of preparatory lemmas that are needed to prepare for these proofs. So we'll have a look at these now. So these are not so much interesting results in their own right, but they're key kind of technical ideas that are needed for the proofs of the two Sylow theorems. Okay. So the first one, and they don't really stand out as telling you, as being interesting in and of themselves necessarily. So lemma 15.5 says if you've got a Sylow P subgroup, capital P of a group G, if X is another element having its order a power of P, so those are the kind of elements that are in P subgroups. If, when you conjugate P by this element, now it's slightly curious here, we've got X inverse PX. You could turn that equivalently, you could make that XP X inverse, because if X has the order of power of P, so will X inverse. Remember, an element and its inverse always have the same order. But for the way it all fits together, it's presented like this. So if the so this is conjugation by X inverse. We got X inverse times P times the inverse of X inverse. So if X is a P element, meaning it has order of power of P, if when you conjugate P by X or X inverse, if you again get P, then the only way that can happen is if the element X was actually in P to begin with. Okay. So let's see what is needed for the proof of that. So certainly you can see by the definition there that when you conjugate P by X or by X inverse, you again get P. So certainly X qualifies as an element of the normalizer of P, okay, because this is the defining criterion for being on the normalizer. P is normal in its own normalizer, so we can talk about the quotient. Okay. And there's quite a lot going on here. X has order of power of P. So when you form this quotient group and look at the element corresponding to little x, so that would be a coset of P. Those are what the elements of the quotient group are. Remember, when we discussed factor groups, quotient groups, and the homomorphism from the original group to one of its factor groups, the order of an element in the image of that homomorphism, the order of an element in the factor group, must be a divisor of the order of the element originally, in the original. So if X started off as having order of power of P, its image, XP, in the factor group must also have order of power of P, okay? Because the order that this element has to be a divisor of the order of X originally. So the cyclic, so what we're looking at there is a cyclic subgroup generated by the coset XP. By the correspondence theorem, which remember describe the things that go on in a group versus the things that go on in a quotient of that group or a factor group of that group. And so that said that any subgroup you see in the factor group is a homomorph, is the image under the quotient, the factor group homomorphism of a subgroup in the original group. So by the correspondence theorem, there is some subgroup of the normalizer which contains P, such that when you do the factor of H by the normal subgroup P, you get this subgroup, subgroup generated by XP. Now, applying what we know about the size of a factor group, the size of a factor group is simply the quotient of the sizes of the two groups, size of H divided by size of P. So when you multiply across by the size of P, you get this equation here. The size of H is the size of P multiplied by the size of the cyclic subgroup generated by X. Now, by definition, these two groups here, well, P was a Sylow P subgroup, so this number here is a power of P. This is the cyclic subgroup generated by XP. It has order a power of P as well. So you're multiplying together two powers of P, so H itself is size, the power of P. So H is a subgroup whose order is a power of P. And secondly, coming from the correspondence theorem, the subgroup H it's a subgroup of the normalizer, it also contains P. But P is a Sylow P subgroup, meaning it's the biggest kind of P subgroup you can have in G. It's got maximal size as a subgroup having size an order of a power of P. So if H is another subgroup having size a power of P that contains P, well, it must be, the only way that can happen is if P is the whole of H, okay? Because P is maximal, a maximal P subgroup, okay? So that's what we say there. P is a Sylow P subgroup containing H, so it must be that actually H is equal to P. But if H is equal to P, that means this factor group is trivial. You're factoring out a group by itself. So you're looking at the cosets in H of H. Well, there's only one coset, H itself. It's the factor group is the trivial group. Okay? So this is the trivial group. So therefore, this one must be the trivial group as well. Okay? But if the cyclic subgroup generated by this is trivial here, it means that this coset XP must be the identity to this factor. Now, the identity here is the coset P. So if XP is the identity, it must mean XP is equal to P. But that only happens, a coset P given by the element X is only equal to P when X is an element from the subgroup P itself. So that gets us our conclusion that X had to be in P. Yeah. Okay. But as in the nature of lemmas, it's not an astoundingly, it doesn't stand out as a particularly interesting result itself, but it's just like a little technical step needed in the other ones. Second one is again technical thing, but it's about counting. Okay? And it concerns remember, we've got an action, we've got the system of subgroups of a certain group, and we've got an action on that set of subgroups by conjugation. This lemma concerns that action. So K is a particular subgroup of G. K is the one you're going to be conjugating. You're going to be constructing GKG inverse. For any subgroup H of G, if you consider the action by the elements of H on K, that's what we're going to consider. The action by the elements of H on K through conjugation. So we're considering the little hk H inverse, every possible element of H. Okay? That produces, again, subgroups of G of the same size as K. They're all conjugates of K. This lemma concerns the number of those. The number of distinct conjugates, we've got this nice expression for it. So this is the index in the group H of this particular subgroup. The subgroup we're talking about is the normalizer of K. So that's a subgroup of G. Instead of all the elements from G that fix K under the conjugation. The intersection of that with the subgroup H and so on. Basic fact about subgroups: the intersection of any two subgroups is a subgroup. So this will be this intersection will be a subgroup, which is a subgroup of H. Okay, so it's an intersection of H. So it's a subgroup of H. So we can talk about the index of it in H. This is the number. Remember, the index of a subgroup in a group is the number of left cosets of the subgroup in that group. Now, any kind of result like this, where you're talking about the number of these things equals the number of things in something else. This index, remember, is the number of left cosets of this subgroup in here, or equivalently the number of right cosets. So this lemma is saying the number of distinct conjugates equals the number of left cosets. In order to prove that, how do you prove that two sets are of the same size in this kind of abstract setting? Abstract algebra. Typically, the way you prove that two sets of the same size is you have to construct a mapping between them. A mapping a mapping that is a bijection, a one-to-one and onto mapping. Okay, and that's how the lemma is proved. Okay, they construct a bijection between these two sets, so namely between the conjugacy classes of K and, yeah, I wasn't sure which side of the cosets. He's choosing the right cosets of this subgroup and the normalizer K intersection H. So we want to take some mapping from the conjugacy classes of K to the right cosets of the normalizer of K intersection H. And it's a pretty naturally defined map. You look at one of the conjugates. Now the conjugation. So this is conjugation of K by H inverse. H inverse K, H inverse inverse, H. This is one of the conjugates. Which right coset of NK intersection H are we going to associate to that? Well, there's really only two choices. We're either going to associate the right coset corresponding to H or the right coset corresponding to H inverse. Those are the only two natural choices, really. Okay, we choose the right coset corresponding to H. So that's our mapping. So all we have to prove then, to prove that there's the same number of both things, number of distinct H conjugates of K and the number of right cosets of that subgroup in H, is to show that that map is a bijection. First of all, it's easy to see that it's surjective. Okay, it's easy to see that it's onto, because we're talking about the conjugates of K by elements of H. So we can, the choice for this little H here is any element from the subgroup H. So therefore, we can definitely obtain as an image any right coset of this subgroup in H. Okay, so there's nothing to prove really. It's clearly surjective. The only thing then is to prove that it's injective. To prove it's injective, we suppose that there are two elements, H1 and H2, that give you the same right coset. Now, the only way they can give you the same right coset is if you can multiply both sides of this on the right by H1 inverse. So you get that H2, H inverse must be actually in the subgroup itself, in the intersection. So in particular, that means it's in the normalizer. H2, H inverse is in the normalizer. So if it's in the normalizer, that means when you conjugate K by H2, H1 inverse, it means you just get K. That's the definition of being in the normalizer, isn't it? So the conjugation of K by this product element, H2, H1 inverse, and then H1, H2 inverse is the inverse of H2, H1 inverse. Remember, the inverse of a product is the product of the inverses, but in the opposite order. So the inverse of that is H1 inverse inverse, which is H1 times H2 inverse. This is equal to K, and then by simply moving the H2s over to the other side, which you do by multiplying on the left by H2 inverse and multiplying on the right by H2, cancels the H2 and H2 inverse from either side there. Puts it over here, H2 inverse on the left, H2 on the right. Then you've got that these are two conjugates of K that are equal. So that proves the map is injective, okay? Because the map is going from the set of conjugates of K to the right cosets. So if we have two right cosets that are equal, they're actually the same conjugate to begin with, okay? So that proves that the map is injective. It's clearly surjective by construction because little h can be any element from the larger group H. So that proves that those two things have the same size because there's a bijection between them. Okay. Any questions about those? Okay. So we'll collapse those proofs there because maybe we can keep them on the same page when we're looking at the Sylow ones. So those are the two technical ingredients that feed in then to the proofs of the theorems. You know, putting off their proofs into separate results means we can keep the size of the argument, down, for the Sylow theorem itself. And you can see they get used in a few places. So lemma 15.6, 15.6, 15.5. Okay, so those are being used in a number of places. So it does shorten the argument down somewhat. So here's the proof of the second Sylow theorem. This is merely saying that all the different Sylow P subgroups are conjugate to one another. Okay? The third one addresses how many of them that there are. Okay? So we set the thing up. We let capital P be a Sylow P subgroup of G. So in other words, G has size P to the R times N. And importantly, remember, P to the R is the maximal power of P. So P does not divide N. Okay? So M is all the rest of the prime factorization of the size of G, of the order of G. Sylow P subgroup, so the size of P is P to the R. Curly S here, curly S, script S is the set of conjugates of this Sylow P subgroup. Beginning, so P1 through Pk, beginning where P1 is this particular Sylow P subgroup itself. Okay? So these are all, these groups, P1, P2, all the way up to Pk, these are all they are all conjugates of P. So they are all subgroups. They're all subgroups of the same size of P. So they are all of them, each of them is a Sylow P subgroup of G. So what we have to prove here is that this is all of them. The theorem claims that all the Sylow P subgroups are conjugate to one another. Okay? So these are the distinct conjugates. Now, how many of those conjugates are there? Well, the lemma we just proved addresses that. The lemma we just proved tells you how many conjugates there are of a particular subgroup when you act on it with elements from the group. It's to do with this index, okay? So we're going to apply 15.16 here, where the choice of H is actually G itself, okay? So when the choice of H is G itself, then we're talking about the total number of conjugates of K there are, as subgroups of G. And this thing here is going to be, this will simplify somewhat to be the index of the normalizer of K in G. So we apply that there. Okay. So the number of these that there are, which is K, this is the index of the normalizer of P in G. Now we already have that this order of G is P to the Rn. By definition of basically Lagrange's theorem, the number of elements in the group is the number of elements in the subgroup multiplied by the number of cosets of that there are. Yeah. Remember the cosets of this subgroup partition the set G. All cells in that partition have the same size. So whatever number of cells in the partition there is times the size of each cell, that gives you the size in the whole group itself, in the whole group G itself. But lemma 15.6 tells us that this number, the index of the normalizer in G, is this number K, the number of distinct conjugates of P that there are. So we've got this result, that P to the R times M is equal to the size of the normalizer times K. Now, remember basic facts about the normalizer we outlined at the start. The subgroup P itself is a subgroup of its own normalizer. Lagrange's theorem tells you that the size of the subgroup divides the order of the containing group. P to the R is the size of the subgroup P. It's contained in this subgroup, the normalizer. So P to the R divides the size of the normalizer. Okay, that's just coming from Lagrange's theorem. He doesn't name check Lagrange's theorem, just kind of keep the size of this down. So in particular, P to the R divides this bit. So the particular bit of conclusion we need here is that P does not divide K. Because remember, P to the R is the maximal power of P in the factorization of G, so there are no more powers of P here. So if all of the powers of p are divided into this part, that means k cannot be divisible by p. Because if it was, then there would be one extra factor of p. You could, at least one extra factor of p we could put to here, p to the power of r plus one of these. So the intermediate conclusion here is p does not divide this number. And now comes the actual proof of the statement. Remember, the statement said all the C log P subgroups are conjugate. Here are all the conjugates of a particular subgroup, C log P subgroup. So we have to prove that this is all of the C log P subgroups. So we do that by considering a general C log P subgroup Q. What we have to do is demonstrate that Q is listed here. Okay? So Q can be obtained from the original starting C log P subgroup P by conjugation. Okay, the way we do that is to again invoke one of the lemmas, 15.6. It's Tuesday, it's just a test. So we consider the action by conjugacy of the subgroup Q on one of these PIs. Okay. Sorry, brain freeze. Yeah, consider these conjugacy classes. These conjugacy classes partition the set X, partition the set S, and the size of each one is given to us by lemma 15.6, okay? Because that said the number of conjugates of a certain subgroup is given by this indexing. The normalizer of that subgroup intersections with the group doing the action, and the index of that subgroup inside the group Q itself. Lagrange's theorem tells us that the size of Q is equal to the index of that subgroup in Q multiplied by the size of that subgroup. So therefore, this index number, this number of conjugates that there are, it's a divisor of the size of Q. But Q is a C log P subgroup. It has size P to the R. So this index, which is the number of conjugates, which is the size of the conjugacy class of the PI, it must be a divisor of P to the R. So the number of conjugates in every equivalence class of this partition is a power of P. We already know P cannot divide K. Now, powers of P are, the P to the 0 is included here. So 1 is a power of P. So we know that the number of conjugates in every equivalence class of this partition is a power of P. If all of them were a non-trivial power of P, then they would all be divisible by P. And therefore, the total number of conjugates that there are would be divisible by P. But a bunch of things, if the size of each cell in a partition is divisible by P, then the total number of elements that there are in the whole set will be divisible by P as well. But we've already proved at an intermediate stage that the number of these conjugates that there are is not divisible by P. So one of those conjugacy classes must be trivial, must contain only one element, which is a power of P, it's P to the power 0. Okay. So one of those elements, let's say it's Pj, is in its own conjugacy class under the action by Q. Well, what that means is we've got an element X from Q, which when you conjugate this particular C log P subgroup, it remains fixed. It's fixed at Pj. But then the first lemma comes. Okay, because Q is a C log P subgroup, every element of it has order of power of P. And that's exactly the conditions for lemma 15.5, that we have an element X of order power of the P, which when you conjugate the C log P subgroup by X, the Sylow P subgroup is fixed. That can only happen when the element X is in when the element X is in the group Pj itself. Okay, that's the conclusion of lemma 15.5. So that means every element of Q, this happens for every element of Q, so every element of Q is within the set Pj. But these are both Sylow P subgroups, so they both have the same size, P to the R. So if one is a subset of the other, they must in fact be equal, because they both have the same size. So if one is a subset of the other, they must be all of it. Okay. So Pj must be equal to Q. So what we've done is we've proved there that one of these conjugates, for any Sylow P subgroup Q, there will be one of these conjugates of this particular starting P subgroup P, which is equal to that Q. So that means this list of conjugates of this particular Sylow P subgroup P is all of the Sylow P subgroups of P. Is all of the Sylow P subgroups of G. So that completes that proof. Then now we know how all the different Sylow P subgroups are related to it. They're all related through this operation of conjugation. This is the action of the group G on its own system of subsets through conjugation. So when I see you this afternoon, we'll discuss the third Sylow P subgroup, third Sylow theorem, which addresses these, gives you these two conditions on this number K, two extra conditions on this number K that there are. In fact, you can already see, we've already in effect proved that K divides the size of G, because we've got it here. The size of G factorized with K as one of the factors, so we've already got that part actually. So the only other part is proving that it's congruent to 1 modulo P itself. Okay. So we'll look at the second, or we'll look at the third theorem this afternoon and look at some of the interesting applications that we can get from it. Okay. So a few applications then this afternoon and a lot more on Friday. We'll get that done. Okay.